Now that we have got an understanding how a particle can move within a magnetic field due to the interaction of its induced magnetic field with the external magnetic field, that causes the particle to undergo circular motion. And so now for the next two videos, we're going to be exploring this idea of circular motion and the magnetic force relationship. And then make sure you watch out all the study bite videos after that section, because there's a lot of ways in which they can test your knowledge of this section here. So we'll make quite a lot of videos on them and make sure we really dig deep so that they won't find that you can fall to the trap. Okay, so let's check out our syllabus connections here. So let's have a look. It says we analyze the interaction between charged particles and uniform magnetic fields. Done. Including the acceleration perpendicular to the field of charged particles. Well, we've talked about that. We said that when a particle moves in a field, it undergoes acceleration and that it's perpendicular to the field. And remember, we used our right-hand palm rule to predict the direction in which that force was acting on a particle. And of course, as we know from previous experience, that's called uniform motion, uniform circular motion. So we're going to do that in this video here. And of course, we're relating it to charged particles. So let's go back to our app that we looked at before, and let's play around with that and get a better understanding of what this dot point is all about. So if we get our fingers coming for me, which is going to be the reverse for you, it's going to be coming out of the page towards me, okay, and then the positive particle is going to be going that way towards the right, so the force is going to be acting downwards, so this particle here is going to curve in that direction like that, okay, and we know that that is a force acting on that, and that force is acting towards the center of a circle. Remember from our right-hand palm rule that the direction of velocity is at 90 degrees to the force acting on it. So here's my particle. If this is the velocity vector, and then we have coming out of the page, we have the magnetic field, and we just change the color again to maybe purple, then going like that is our force. And that is the force that's causing the particle to curve downwards. And of course, that is the net force on the particle. So therefore, that is the centripetal force, right? FC. So when we're talking about in that dot point, I'll just flick back for you, where it talks about the acceleration of a particle, right? Well, this particle is accelerating because it's changing direction. Even though its velocity is constant, it's undergoing uniform circular motion, and so therefore it's changing direction. So the acceleration that it's experiencing is the centripetal acceleration, which is v squared on r, as we know. If we flick back again, it says perpendicular to the field. Well, yes, the force is perpendicular to the field, and you can see here in this diagram that this angle here is 90 degrees. There's the direction of the field, there's the direction of the force, so it's perpendicular to the field. And we're going to see that that is the case with our next video when we talk about this force, which we said is the centripetal force, is also experienced with FB equals QVB, right, where that is parallel to the velocity, exactly the same sort of idea there. So let's explore this relationship here of FC. Remember, FC is equal to mv squared on r. So let's use our app now. Let's manipulate some variables and see what we get with the relationship here, this centripetal force, and the effect it has on the other variables. So let's have a look here. Mass. We can change the mass, and we've got mass in the equation. We can change the velocity. Now we're going to keep the force constant, because we're going to look at the effect on the radius, right? So we can see down here the radius is being shown at the moment. So if I rearrange this equation, I can say that the radius is equal to mv squared on fc, okay? And so there's an inverse relationship there. So let's have a look at the effect of mass. If I increase the mass, what happens to the radius? So everything else stays the same. So let's go start. There it goes. Pew. All right, so that's it with that mass. What happens now if I increase the mass? Well, according to our equation here, right? If I increase the mass, then our radius should also increase if everything else is kept the same. Let's try that out, okay? So that's that one. It would be nice if we could, we might be able to do 2 on 1. Let's try it. So if I increase the mass at 6.2 at the moment, so let's crank it up to as far as it goes, 10, and go start. And look at that. The radius has increased because the radius of curvature is larger. So we just showed that if you increase mass, you increase the radius. And so therefore with this relationship, how I've written it there, R is proportional to mass. Alright, so that makes sense for that equation there, but if we look at the other equation, this one here, that relationship is not the same, right? Let me explain. Right, here in this bottom one we said as R increases, mass increases, and we saw that with the applet there, right? However, if I keep FC the same number, let's say 100, right? If I increase the mass, I cannot increase the radius here, because if I increase the numerator and the denominator with velocity staying the same, then that FC value is going to go up. We can't have that. So the mass has to increase, means the radius has to decrease. Okay, it's an inverse relationship if we're keeping the force the same. So if I look back over here now, how was it that the applet showed that we increase mass and we increase radius and increase mass? Well, we kept velocity the same, there it was, right? We can see it on here, velocity is the same, but the strength of our centripetal force must have changed. So if we increase the radius, okay, that means the mass was increased because we changed the mass, but the centripetal force would have to have decreased. And that makes sense, because if you think about it, if a particle is coming out, if you decrease the centripetal force, that is the force acting on the particle to change its direction, if you decrease that, that means it takes longer to take a curve, which means its radius increases. And that's what we saw. So be very, very careful when you interpret equations, and that you have to be able to explain what's going on, because this ability to look at an equation and interpret it is very, very important, as we're going to see in a lot of the questions coming up with study bites. Okay, so just a quick recap. We said that charged particles undergo circular motion when they're in a magnetic field. That we related to our circular motion equation, Fc equals mv squared on r. We then looked at some relationships within our formula there by playing with this app and making predictions on the effect of changing variables on the radius, for example. So I want you to go ahead and do that, and I'll see you in the next video. Right, before we go to the next video, I want you to check out more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.